the noise analysis in CW modulation. Now, noise analysis in CW modulation. Now, in the previous class, I have discussed the noise analysis in amplitude modulated signal. Okay, so amplitude modulated signals. So I have discussed the noise analysis, that is DSBC signal, HSB signal, and the envelope detector, that is the conventional AM signal. So I have discussed the noise analysis. Now here we have to consider that the noise is a wideband Gaussian type noise, an additive wide Gaussian type noise. So we have to consider, and also we have to consider that here one bandpass filter is used as a receiver input. That is the that can tune a particular band of frequency and reject the unwanted band of frequency. Now today I discuss the noise analysis of angle modulated signals or the FM signals. So noise analysis. So noise analysis of noise analysis of FM signal. Noise analysis of FM signal. So noise, in case of noise analysis of FM signal, so FM receiver model is there. So first I will draw the FM receiver model. So that is FM receiver model. FM receiver so FM receiver model. So here this is almost same as the AM receiver model, but here one extra part is there, that is that can remove the amplitude variation. Okay, so so in FM receiver model, so first one adder circuit is there, that so where the FM signals, that is ST is the FM signal, and along with the white noise, that is WT, is added in the receiver. Now this receiver, so here one bandpass filter is there, bandpass filter, and it is also known as the intermediate IF filter or intermediate frequency filter. So this is a bandpass type. So bandpass filter, that is this is IF filter. So the function of IF filter is same, that is so it consists of a tuning circuit that can tune a particular range of frequency. Now, so output of that, so this is the noise is narrowband. So noise is narrowband, and after that it is passed through the one limiter circuit. So limiter circuit, why it is used? Now to remove the amplitude fluctuation of the FM receive signal, because in case of FM signals the amplitude fluctuation is not considered, because in FM the amplitude should be constant. Amplitude should be constant, but frequency should be variation or phase, frequency or phase. Now, now in case of remove the amplitude variation, so one limiter circuit is used. So the function of the limiter to remove the amplitude fluctuation of the receive signal. So this is the function of the limiter. Okay. Now output of the limiter is passed through the demodulator, that is the discriminator. So FM discriminator. So output of the demodulator, or it is also known as the discriminator. So discriminator, that is, this is also the demodulator. And after output is after that it is passed through the low pass filter. And low pass filter, the cutoff frequency of the low pass filter is equal to the message signal bandwidth. So that is here the low pass filter. So if the message signal bandwidth is W, then the cutoff frequency of the low pass filter is W. Okay, so a low pass filter, that is the cutoff frequency of the low pass filter is same as the frequency of the message signal, and here the output can be obtained output. So this is the receiver model. So standard FM receiver model. So in FM receiver model, here actually the input signal, that is the input signal is received by the receiver, and along with these input signals some unwanted signal is also received by the receiver, and these unwanted signals are known as the noise signal. So this noise signal is a wide band Gaussian type noise signal. So that's why we have to write down here that WT, that is white noise. White noise is assembled in the signal, that is SC. And after that, it is passed to the band pass filter, that is IF filter. IF filter is used. So IF filter is basically one ideal band pass filter, and that means it has a range of frequency and through which the input signal is passed, and outside this range of frequency it is rejected. And as a result, the output of the band pass signals is a band limited of the noise. So noise will be narrow band at the output of the band pass filter, and after that it is passed through a limiter. So function of the limiter to remove the amplitude variation of the input signal. So if input signal has amplitude variation, then it can remove this by using the limiter. And after that it is passed through the demodulator, that is FM demodulator. So FM demodulator is also known as the FM discriminator. So FM discriminator, and after that it is passed through the low pass filter, and low pass filter cutoff frequency is same as the message signal frequency. So the cutoff frequency of the low pass filter is same as the message signal frequency. So if the message signal frequency is W, then the cutoff frequency of the low pass filter is also the W. Okay, so this is the standard FM receiver model. And in this model, by using this model, we have to calculate the noise analysis of FM signal. Noise analysis of FM signal. Now, band pass filter. So, band pass filter. So, band pass filter output. So, output is known as the XT. So, XT contains two, that is ST plus NT. NT is the narrowband noise. NT is the narrowband noise, and XT, and output of the demodulator, that is, this is the VT. So VT is the demodulator output. So VT is the demodulator output. Demodulator output means this is a discriminator output. Okay. Now we have to calculate the theoretical analysis of the FM receiver by using the noise. Okay. So first we have to write down the modulated signal, that is FM modulated signal. So first FM modulated signal. So equation of the FM signal ST equal to AC into cos of 2 pi FCT plus phi t. Okay, so this is the FM modulated signals. So standard FM, already you have known this this equation, and phi t is the instantaneous phase. So phi t is the instantaneous phase, and this phi t equal to 2 pi kf into 0 to t into mt dt. So this is the standard FM signal, that is the generalized form of the FM signal. Okay, generalized form of the FM signal. Now the noise. So noise, this is a white noise, and this white noise when passed through the band pass filter, so it is a narrow band filter, and narrow band filter. So NT can be written as, that is the noise NT. NT can be written as, so band pass filter type, that is N of IT into cos of 2 pi FCT minus of N of QT into sine of 2 pi FCT. While NIT, this is the in-phase component of the noise, and NQT is the quadrature component of the noise. Okay, so and noise is a band pass type noise because the white noise is passed through the white noise, WT is passed through the band pass filter, and then the output of the band pass filter is the narrow band type noise, and narrow band type, and it has a in-phase component and one quadrature component is also there. Okay, in-phase component and quadrature component. Now, if we write down this equation NT in terms of the polar coordinate, then it can be written as RT into cos of 2 pi FCT, cos of 2 pi FCT plus psi t, where RT equal to root over of, that is magnitude part, that is of n I square plus n q. Okay, and psi t equal to tan inverse of b by a, that is n of qt by n of it, n of qt by n of it. Okay, n of qt by n of it. Now from these two equations, we can write down that n of it, that is in phase component n of it equal to RT into cos of psi t, and n of qt equal to RT into sine of psi t. Okay, so this is the calculation of the noise. Now our aim to determine the figure of merit at the output of at the receiver output. This is our aim to in this case, our aim to determine the figure of merit at the receiver output. Okay, so receiver output figure of merit. So figure of merit equal to the SNR input, SNR output by SNR input. So figure of merit. So this is our aim to determine the figure of merit. That is SNR output by SNR input. So to determine the SNR output, so we have to calculate the signal at the output of the FM. That is our aim to determine the FOM, figure of merit. So FOM equal to the SNR output by SNR input. Okay, so this is actually our aim to determine figure of merit of the FM signal or FM modulated signal. Now to determine this, so we have to see the receiver model. So here XT is there. So XT contains the signal power and the noise power. So you have already noted signal power. Signal power equal to AC square by 2, and noise power, this is the N0 into W, N0 into W by 2. So now to determine the output noise power. So output SNR. Now so output SNR. So in case of output SNR XT, so XT is the, so we have to write down XT. So XT equal to input of the demodulator, XT equal to ST plus NT. XT equal to NT plus ST plus NT. Now ST plus NT. So write down this ST plus NT. So if we write down ST plus NT, so we have to write down this, that this is equal to ST value is AC into cos of 2 pi FCT plus phi t plus RT integral to RT cos of 2 pi FCT plus psi t. RT into cos of 2 pi FCT plus psi t. Now we have to draw the phasor diagram of the resultant output, that is xt. So if we draw the phasor diagram, then we can see that. So here the AC, so first AC, and now this is equal to RT, and this is equal to resultant signal xt, and this is the theta t minus phi t, and this is actually the psi t minus phi t. But theta t is the resultant phase. Theta t is the resultant phase. So theta t can be written as phi t plus tan inverse of RT into sine of psi t minus phi t by AC plus RT into cos of psi t minus phi t. So this is the theta t. Now here actually the in this case we have to consider only the case of phase variation, not the amplitude variation. Only we have to consider the phase variation. So phase variation, so we have to consider. So This is theta t. Theta t is the resultant phase. Now theta t equal to this. Now, so in this case, we have to consider only. So in case of FM, we have to consider only the phase variation. That is, envelope of xt is not, or so in this case, the envelope of xt uh, is not considered here. Is not considered here because in FM only we have to consider the phase variation, phase part, not the amplitude variation. That is the for envelope of xt is not considered here. Okay, so because of FM calculation we have to consider only the phase variation theta t. Okay, so only so FM phase variation theta t. Now we have to consider. That's why we have to consider theta t. So theta t equal to the phi t plus of tan inverse RT into sine of psi t minus phi t by AC plus RT into cos of psi t minus phi t. So this is our consideration, because in case of FM the amplitude variation is not considered, only the phase variation is considered. So that's why you have to consider the theta t. Now here the two cases are one. So here one cases are there. Now if the amplitude of the carrier signal, that is the AC, is if the amplitude of the carrier signal is larger than the noise, that is noise signal, then the CNR, that is carrier to noise ratio, will be very much greater than unity. So if AC, that is if the amplitude of, so first consider that amplitude of carrier signal, amplitude of carrier signal, that is AC, is larger than amplitude of the noise signal, than amplitude of noise signal. Amplitude of noise signal means magnitude of noise signal means RT. Okay, so amplitude. So that is if CNR, input CNR, that is CNR, that is carrier to noise ratio, that is carrier to noise ratio is very larger than 1. That is CNR is larger than 1. So this is the first consideration. That is if the amplitude of the carrier signal, that is AC, is larger than the amplitude of the noise signal RT, then the CNR will be larger, because the noise is if the noise amplitude is smaller than the carrier signal, then CNR will be larger. So if CNR is larger, then we have to consider that theta t will be, so theta t so theta t will approximate at RT phi t plus RT into sine of psi t minus phi t divided by AC, So RT sine of psi t minus phi t by AC. So so in this part, so this is the signal part. This is for signal part, because phi t contains the message signal, and this is the noise part. So inside the noise part, signal part is also included inside the noise part. Okay. Now we have to write down this, that is 2 pi kf into 0 to t mtdt plus RT by AC into sine of psi t minus phi t. Okay, so this is the theta t, that is input of the demodulator. Now we have to consider that the discriminator output, that is the FM demodulator output, the FM demodulator output. So FM demodulator output can be written as output can be written as FM demodulator output, that is VT. So FM so here FM demodulator output, that is VT. VT can be written as VT equal to, so VT equal to 1 by 2 pi into d of theta t dt, d theta t dt. Now we have to put the theta t value, that is this is equal to 1 by 2 pi into 2 pi kf into mt dt plus RT by AC into sine of psi t minus phi t. Now this is into ddt. So ddt of this. So ddt of this equal to, so that means kf into mt first part plus 1 by 2 pi 1 by 2 pi into AC, 1 by 2 pi into AC into ddt of into sine of ddt of ddt of RT into sine of ddt of RT into sine of phi t minus phi t. Now this is equal to kf mt plus n dt, where n dt, that is the noise part and the signal part. So this is the demodulator output. Now here actually the psi t is uniformly distributed. So here where n dt, where n of dt, n dt equal to 1 by 2 pi AC into d dt of RT sine of psi t minus phi t. Thus, we can provide the carrier to noise. So, actually, this is the case when CNR, that is carrier to noise ratio, is high. Now, the discriminator output VT consists of it. So, when CNR is high, then the discriminator output VT consists of a scale version of the original maximum signal, that is KF into MT, plus the additive noise part, that is the NDT. So additive noise part, that is NDT. So scale version of the message signal plus the noise part. Now we have to use the output SNR. Actually, output SNR can be defined as the quality of the performance of the FM receiver. Quality of the, so output SNR can determine the quality of the FM receiver. Now so here actually psi of t. So psi of t. So psi of t. So psi of t, in this case, psi of t is uniformly distributed over 2 pi radians. Psi of t is distributed uniformly. Psi of t is uniformly, so uniformly distributed. Psi of t is uniformly distributed over 2 pi radians. Therefore, the mean square value of NDT, so the mean square value of NDT will be biased by masses dependent part phi t. So here, actually, if we determine the noise power, so actually our aim to determine the output signal to noise ratio. So for obtaining the output signal to noise ratio, here the signal part can be obtained. This is the signal part and this is the noise part. So when we have to determine the noise power, then first we have to determine the mean square value of the noise power. Now when we have to determine the mean square value of noise power, then we can see that in NDT one phi t part is also there. The presence of phi t produces a component in the power spectrum of the noise. So because due to this component, so when we have to determine the PSD of noise component, then it can also produce some component. Okay, but therefore the frequency component do not appear, but this component, so this component will be eliminated by using the low pass filter. Okay, low pass filter. So we have to write down this. So psi of t is uniformly distributed over 2 pi radians. Now, when we have to determine the power, so to determine the noise power at the output of the demodulator, to determine the noise power at the output of demodulator, to determine the noise power at the output of demodulator, we have output of demodulator, we have to do the mean square value. So we have to determine the mean square value of NDT. Determine the mean square value of NDT. NDT and NDT which contains the component of component of phi t, because phi t which contain the component phi t, but due to the use of the use of low pass filter, and this component will be eliminated. Component will be eliminated. Okay, and as a result, the NDT can be written as N of dt. So N of dt, that is output of the receiver, NDT, that is noise output, that is 1 by 2 pi AC into ddt of RT into sine of psi t. Sine of psi t. So RT sine of psi t. So what is the value of RT sine of psi t? So RT sine of psi t equal to this one. That is RT sine of psi t. That is this mean MQT, that is quadrature component. So it can also written as that 1 by 2 pi AC into ddt of MQT. So NDT equal to, so NDT equal to this one. So that is, this is the noise component. NDT equal to this one. Now we have to determine the power spectral average noise. Actually, now to determine the average noise power. So this is the noise signal at the output of the demodulator. Noise signal at the output of the demodulator. Now we have to determine the signal to noise ratio. To determine the signal to noise ratio, so here to determine the noise power, average noise power of the discriminator output. So here one part is there, that is differentiation with respect to T part is there. Now the power, first we have to determine the power spectral density of the noise, output noise. So power spectral density of the output noise. So that is power spectral density. So we have to determine the noise power. Noise power. Determine noise power. Noise power. So to determine the noise power, so first we have to determine the power spectral density PSD of NDT. PSD of NDT, this is equal to S of NDF. S of NDF. So here one formula is there, that is S of F square into S of NQF, that is quadrature component NQF. Okay, so NQF, that is, so where HF is the H of F, this is the H of F, this is the transfer function, and this is the differentiator transfer function, ddt of this differentiator transfer function, and here input is n of ut and output is n of dt. So n of dt, so n of dt, so n of dt, so n of dt equal to AST convolution of NQT, or we can say that n of df HF into NQF, and or HF equal to n of df by NQF. So here HF equal to J2 pi f, because differentiator J2 pi f, HF equal to J2 pi f. So we have to write down J2 pi f. That is, we have we can write down the total NDF. So transfer function is J2 pi f by 2 pi AC, because here 2 pi AC. So if we write down this is the different J2 pi f, and 1 by 2 pi AC. So so NDF by NQF. So this is equal to 1 J2 pi f by 2 pi AC. So this is equal to 2 pi cancel out, 2 pi, so only JF by AC. So JF by AC, so this is the HF equal to JF by AC. Okay, HF equal to JF by AC. So we have to write down this is equal to JF by AC whole square, JF by AC whole square into S of N of QF, S of N of QF. Now this is equal to, so this is equal to F square by AC into S of NQF, S of AC square. S of NQ wave. Now we have to determine S of NQ wave to know the value of S of NQ wave. S of NQ wave. So in the previous class I have discussed that S of NQ wave. S of NQ wave equal to N0 because S of NQ wave equal to N0. So S of NQ wave, that is the power spectral density of the quadrature component of the noise. So this is the power spectral density. So quadrature component of noise. So if we draw, so in the previous class I have draw the power spectral density of quadrature component. So if we draw this, that
স্যার
uh,
ওটা মাইনাস হবে না? মাইনাস এফ স্কোয়ার বাই এ স্কোয়ার এসি স্কোয়ার।
uh, actually this is mod value. mod value আছে বলে মাইনাসটাকে ডিলিট করে দিচ্ছি। ঠিক আছে, এই যে
ওকে স্যার।
এই যে মড ভ্যালু আছে বলে মাইনাসটাকে কাউন্ট করেছি। তো অনলি দা পজিটিভ পার্ট, তো এফ স্কয়ার বাই এস স্কয়ার। এবার হচ্ছে যে নাও দিস, so here we have to consider, this is a band pass filter. Okay, so this is a band pass filter. Band pass filter means, so here the transfer function of this filter, is like this, that is uh, this one, that is bandwidth is B, and this is the FC, and this is minus FC, and this is B, and this is the transfer function H of IF, F, that is H of IF. Okay, so band pass transfer function. Now we have to so when the noise is all, when WT pass through the these types of filter, then WT is also limited with this transfer function. Okay, WT, that is noise, is also limited to this transfer function. Noise is also limited to this this transfer function, and that so here we have to write down this one, that so draw this one, that is here the noise component. So, so in the previous class I have discussed this one, that is S of n. So we have to consider S of n. S of n, that is noise. So S of n equal to same, that is if this is the FC, so this is B, this is B. Okay, so noise part. Now this is the noise. So noise contain the two parts. That is, one is the quadrature component, and here actually this is N0 by 2. That is power spectral density of the noise, white noise. Already you have know that power spectral density of the white noise is N0 by 2. This is a fixed value. Now, when it is, so this is the noise. Now, here actually our requirement is quadrature component. Now to obtain the quadrature component and the in-phase component, so we have to transfer these band pass types of signal into the low pass signals. That is low pass signal, band pass to low pass signal. So we can write down this one. Can write down this one. Write down band pass to low pass transform. Band pass to low pass, band pass to low pass transformation, and band pass to low pass transformation. Then we have to write down this is equal to B by 2, and this is minus B by 2. Okay, and here actually this is the S of NQ if NQF, and here this value is N0, this value is N0. Okay, so this value is in, so actually this portion I have discussed in case of PN block or band pass signal representation of signal system. Okay, so when we have to transfer from the band pass to low pass signal, so then we can obtain this value, that is B by 2, and so here actually the FC plus B by 2, here actually FC plus B by 2, and here FC minus B by 2. Okay, and when band pass to low pass transformation, then we can obtain this one, that AS of NQF and N0 into this. So S of NQF equal to this. Now actually our aim to determine the power spectral density of the output noise. Output noise. So here that this part is multiplied with the SQF. So where so this is actually the power spectral density of the quadrature component, noise quadrature component. Now power spectral density of the, now we have to determine the power spectral density of output noise. So output, so 1 square per, so f square by ac square is there. So f square by ac square is there means, so these types of output can be obtained. Output. So that is one curve type. So we have to draw so this is actually the S of ND, S of NDF. Okay, and this is minus B by 2 to plus B by 2. And when it is passed to the low pass filter, when it is passed to the low pass filter, that is after passing through the low pass filter, the nature of the signal is same, but bandwidth is so this is actually the minus W to plus W. So this is S of NDF. দেখো বুঝতে পারলে কিনা যে actually low pass filter, so this is actually the discriminator output. Okay, discriminator output, and when it is passed to the low pass filter, so output of the discriminator is the input of the low pass filter. Now low pass filter cutoff frequency is the cutoff frequency of the message signal. Now where W is the bandwidth of the message signal. Bandwidth of the message signal. W is the bandwidth of message signal. Now we have to write down. So this is the noise part. That is, this is the white noise. Now this is the quadrature component of the white noise, and now this is the discriminator output, the PSD of discriminator output, and this is the PSD of low pass filter output. Low pass filter output. Okay. So low pass filter. So first one is the PSD of the white noise. Second one is the PSD of the quadrature component. Third one is the PSD of the output of the discriminator, and fourth one is the PSD of low pass output of the low pass filter. Okay, low pass filter output. Now we have to determine the expression. So here actually S of ND can be obtained. Now S of ND. So after passing through the so S of ND. So S of ND. S of NDF. this is equal to, so limit band limited signal, that is f square by ac square into s of n cube equal to n0, that is this is equal to n0. When this is equal to n0, so n0, and if where if is less than equal to w and 0 or otherwise. So this is actually the NDF, that is the output noise at the low pass filter output. So that is output PSD, a low pass LPF out PSD of the LPF output, low pass filter output. Okay, so this is the power spectral density of the low pass filter output of the noise. Now, obviously noise. Now we have to determine the noise power. So, what will be the formula for noise power? The noise power, that is the integration of PSD, is the noise power. So the noise power. So noise power. This is equal to, here the limit is minus W to plus W, and S of N df df. Okay, so we can actually it is written as S of ndf. This is also known as the S of n0f. S of n0f বলো, S of ndf টা ঠিক হচ্ছে না, S of n0, that is the output power spectral density, আর discriminator output হচ্ছে S of ndf, discriminator output, this is equal to f square n0 by ac square when f is less than b and 0 for other one. B not b by 2. Okay, f of b by 2, and this is the output the noise output. So this is equal to s of 0. Now determine this value. So determine this value. This is equal to, so minus w to plus w, So this is equal to n0 into f square by ac square. This is square into df. Now this is equal to what was the value? n0 into f square by ac square. So n0 by n0 by ac square. This is constant, and only minus w to plus w, f square df. So f square df. So you can calculate this value. This is equal to 2n0 into wq by 3 ac square. So noise power. So this is the noise power. That is P of the noise output noise power. That's a output noise power. Now output signal power. So next the output. So this is the noise power. So we have to calculate noise power. Now next the signal power. Next the output signal power. Output signal power. output signal power কি ছিল না output signal, so kf into mt, kf into mt, so kf into mt, so kf into mt means uh, one another observation is there, that is output noise power P of n0. This is proportional to 1 by Pc. Pc means carrier signal power. Because AC square by 2. This is equal to AC square by 2. That is the output noise power is proportional to the output noise power is inversely proportional to the carrier signal power. Okay, so in this case, so carrier signal power, that means if the carrier signal power is increased, then the output noise power is decreased. Okay, so this is one important part of the FM, that if the carrier signal power is increased, then the output noise power is decreased. Okay, so output noise power is decreased, carrier signal power is increased, then output noise power is decreased. Next we have to write down the output signal power. Output signal power means, so output signal power, that is output signal power here. So what is the output signal power? The case output signal power, that is P of signal output, P of SO equal to F square into P, where P is the mean square value of massive signal. So mean square value of MT. So signal to noise ratio, so SNR output, so K of F square into P by 2 into omega q into n0 into 3 AC square. That is 3 AC square into KF square into P by 2 N0 into omega WQ. So this is the output noise, SNR at output. So this is actually the SNR output. Now SNR input. So SNR input, or so SNR, this is the SNR output. Now SNR, so SNR input, SNR input. So SNR input is noise power. So here the signal input. So signal, so carrier, actually the carrier signal, so signal, so SNR input, that is the carrier signal power. So signal power, so signal power, input signal power equal to AC square by 2, and the noise power, input noise power. So it input signal power or input carrier power is same. input carrier power or input signal power is same. So noise power, input noise power equal to W into N0, W into N0. Okay, so actually in case of FM, the carrier power and signal power is same. Already you know that in case of FM, the carrier power and signal power is same. So SNR input is also known as the signal to noise ratio. So it is also known as the channel signal to noise ratio. So SNR input is also known as the. So in case of FM, this is also known as the channel channel signal to noise SNRC. That is, this is known as the channel signal to noise ratio. This is equal to AC square by 2 N0 into W. Okay. So in case of FM, the carrier signal power or the channel signal to noise ratio, this is same. Okay. So that's why it is also known as the SNR input. SNR input means SNRC. So the FOM figure of merit is equal to SNR output by SNR input. SNR input. Okay. So SNR input that is SNR output equal to this one, that is 3 AC square KF square P. So 3 AC square KF square P by 2 N0 2 N0 into W2 into SNR input is AC square. So W0 in W into N0 by AC square. So AC square is cancel out. AC square cancel out, and 2 N0 is cancel out. 2 N0 is cancel out. W. So this is equal to KF square by 3 KF square by W square into P. Okay, so figure of merit. So figure of merit equal to 3 KF square by W square into P. So where P is the mean square value of the message signal. Okay, P is the mean square value of the message signal. So FOM of FM equal to 3 KF square by W square into P. Okay, now if we consider that sinusoidal message signal, if the message signal is sinusoidal, then sinusoidal wave. So now for special case, so if we consider that for sinusoidal message signal, with frequency band. with frequency FM, then that is if MT equal to AM cos of 2 pi FMT.
Hello.
So we have to put the mean square value, that is P equal to M square by 2, M square by 2. So FOM equal to 3 K square by omega square into M square by 2. So now if we compare this FOM with the AM, then we can consider one case. One case that if now we have to consider the case of sinusoidal wave frequency of FM or modulating wave, and as if if we consider one FM signal with the frequency one message signal of frequency now if we consider a sinusoidal wave of FM. FM is the frequency of the modulating wave, and del F is the frequency deviation. Del F is the frequency deviation. Now, ST can be written as S of t equal to AC cos of 2 pi FCT plus del F by FM into sine of 2 pi FMT, sine of 2 pi FMT. Now, sine of 2 pi FMT. So this is equal to now again actually you have phi t equal to 2 pi kf into mtdt. So this is equal to now this is equal to del F by Fm into sine of 2 pi FMT. This is phi t. Now differentiate with respect to t. Then we can say that mt can be written as So mt equal to del F by kf into cos of 2 pi fmt. So the average power P equal to del F square by 2 kf square. P equal to this. Now SNR output, this is equal to SNR output equal to 3 kf square into P by W square. So now put this value, that is 3 into AC square into del of A square by 4 into N0 into W. Now this is equal to 3 AC square into beta square by 4 N0 into W. Where beta equal to so SNR out. So beta equal to del F by W. Del F by W equal to beta. Beta equal to del F by W. Now SNR output by SNR. Next SNR output by SNR input. This is equal to 3 by 2 into del F by W square. So this is equal to 3 by 2 into beta square. So FOM, so the figure of merit, so the figure, so this is equal to FOM, figure of merit. So figure of merit, this is the FOM of FM. FOM of FM. Now FOM of FM. Now in case of AM for ideal AM or in ideal AM modulation, the FOM equal to 1 by 3. So 1 by 3. So already I have discussed that for ideal AM modulation means mu equal to 100 or 1, mu equal to 100%. So FOM equal to 1 by 3. Now if we compare this, then you can say that 3 by 2 beta square greater than 1 by 3. So or beta equal to beta greater than 0.25. That is we have to consider beta equal to 0.25. 0.2. That means that based on the noise consideration, that is the improvement factor. That is the modulation index. So if beta is 0.5, then the distortion, that is the distortion FM is minimized. That is why actually if beta is greater than 0.5, then distortion in FM is minimized, and this is actually the amplitude distortion, and the phase distortion will be minimized if beta is greater than 0.5. Beta is greater than 0.5 because here it is converting to the wideband effect, and if beta less than 0.5, then it is considered as a narrowband effect, and as a result it is the amplitude distortion and harmonic distortion is good. So this is actually for special consideration for along with the in AM signal. So here actually our aim to determine the up to this. Okay, so that is the figure of merit of the FM signal, and this is the case when Sienna, that is the carrier to noise ratio, is greater than 1. So this is the case when CNR is 1. CNR is 1, so here we have to consider when CNR is 1. So this consider the amplitude of the carrier signal is larger than the amplitude of the noise signal. So this is the case 1. Case 1, then at that time that the FOM equal to this. But when CNR is less than 1, CNR is less than 1 means that when the amplitude of the noise is more than the amplitude of the carrier signal, then what will be the phenomena in this case? Now, this case, so second case, so we have to consider the second case. When the carrier, when the CNR is, when CNR is less than 1. That means the noise amplitude is greater than the carrier signal amplitude. So that is the noise amplitude is greater than or much more greater than carrier signal amplitude. Then what phenomenon occurs in this case when CNR is greater than? So in this case, in this case, FM, that is actually the FM threshold effect. So FM threshold effect. So that is the noise amplitude is greater than this. So we have to consider. So we have to consider this. That is xt equal to AC cos of omega ct plus phi t. So in this case, noise is also considered as ST because noise amplitude is also greater than this xt equal to AC cos of omega ct plus phi t plus nt, and where nt equal to RT into cos of omega ct plus psi t. Omega ct plus psi t, and xt can be written as this. Xt can be written as AC cos of omega ct plus phi t plus RT cos of omega ct plus psi t. Now, if we write down in terms of the polar coordinate, then this is equal to ET into cos of 2 pi FCT plus phi t plus beta t. Now, where beta t, actually in case of FM, we have to interest about the phase, not interest about this amplitude, that is in graph. Okay, in case of FM, so only we have to interest this phase one, that is this phase part, not interest about the amplitude part. In case of, so that's why where beta is approximately tan inverse of AC into sine of phi t minus psi t by RT. Because here RT is greater than, actually RT here R of t is greater than AC. R of t greater than AC. That is noise part. RT is the noise part. So RT is greater than AC. So that the FM, so VT, that is the discriminator output. So discriminator output VT, VT equal to ddt of 2 pi FCT plus psi t plus beta t. So actually this is AC by RT into sine of phi t minus psi t. So ddt of this, so this is equal to 2 pi fct, that is this is equal to 2 pi fct fc plus d of psi t dt plus d of beta t dt. Now here the term d of psi t corresponding to the, so this is actually the noise part. This is actually the noise part, and the only part and the information. So beta t here, the beta t consider the information. So this term contain the information part, but we can see that, so actually beta t contain the information. So we have to write down. So among the this output, beta t d of dt beta t contain the information. Contain the information. Contain the information, and again beta t again proportional to beta t again proportional to 1 by RT, 1 by RT this one. So 1 by RT, beta t is proportional to 1 by RT. That is RT means noise portion, noise signal 1 by RT, which is the noise signal. RT is the noise signal. Thus we can say that d beta t dt does not contain any signal term that is directly so does any signal term that is output is a noisy part. So total output. So on the total output, we can see that we cannot we cannot extract the message signal from the output, because output contains all the noise part. So that is the output is the distorted version. Output is the distorted version. So when CNR, that is carrier to noise ratio, is very less than 1, then the output of the FM contain the noise distorted signal. That is the message signal is distorted. That is, we cannot extract the message signal from the output. Okay, so from the output we cannot extract, we cannot get the output from the output signal. That is all the noisy output signal, we can obtain the noisy output signal. Okay, so hence we are the signal, all the signals are distorted at the output when CNR is very less than 1. That is the carrier. So CNR is less than 1, then the output is distorted at distorted output. That is, from the distorted output we cannot extract the message signal. So we can conclude some limited value is there. So before which we can conclude that some limited value is there, before which the output signal is distorted. Okay, and this limited value is known as the threshold effect. So threshold effect. So threshold value. So limited value is the threshold value. So we are below the threshold value, the output is distorted. So threshold value means some particular limited value, and below which the output is distorted. Below which the output is distorted. So this effect is known as the threshold effect. Okay. So threshold effect means so this is a value, and below which the output signal is distorted. Below which the output signal is distorted, and this value is known as the threshold value. Okay, so this value is known as the threshold value. So and the total effect is known as the threshold effect. And but in case of N, the for envelope detector, the threshold effect is arise for envelope detector. But in case of Orion detector, the threshold effect is not arise. Always, so you have to remember that threshold value means below which the value below which or minimum value or value below which the output is distorted. Output is distorted. Value below which the output is distorted is known as the threshold value, and the total effect is known as the threshold effect. But in case of coherent detector, this threshold effect is not arise in case of coherent detector. Coherent detector, no threshold effect. No threshold effect. Threshold effect means all the signals are distorted. Output signal is distorted. So output signal is distorted. So, so this is the threshold effect. Now this threshold reduction. So if this is the threshold effect of the FM signal. Now threshold reduction. So how we can remove this threshold effect? So FM threshold reduction. Threshold reduction. So threshold reduction. FM threshold reduction. Now threshold reduction can be can be obtained by modifying the FM demodulator by using a negative feedback by connecting a negative feedback to remove this threshold reduction. So now threshold effect can be removed by using using a negative feedback. Negative feedback commonly known as the FMFB or using a phase lock loop demodulator. So threshold effect can be removed. Threshold effect can be removed. So threshold effect can be removed by using by using a negative feedback or by connecting a negative feedback to the FM demodulator by connecting a negative feedback in FM demodulator. Or using phase lock loop. Okay. So connecting negative feedback, that is in case of threshold reduction. So here actually one product modulator and one IF filter and limiter meter and discriminator, FM discriminator, and low pass filter, and output of this low pass filter is connected to a negative feedback system, that is here generally VCO is used, VCO, and this total, this is actually known as the mixer circuit. This is FM wave and this is output signal. And the total configuration is known as the FM feedback modulator, FM FB demodulator. FB means feedback demodulator. FM feedback modulator, demodulator. So this system is known as the FM demodulator. So this system is used to remove the threshold effect. To remove the threshold effect. So and this is known as the FM FB demodulator. That is one feedback part is connected, and so here the local oscillator is replaced by a voltage control oscillator. So to remove the threshold effect. So this is the removation of the threshold effect. Okay, threshold effect means threshold effect means below which the FM is distorted, the output signal is distorted. So this effect is known as a minimum value of the carrier to noise ratio, below which the output is distorted is known as the threshold effect. Okay, so threshold effect. So this is the threshold effect. Now another part is there, that is the capture effect. Capture effect. So here one question is there, that is what is threshold effect in FM? What is capture effect in FM? So this is short type question. So capture effect. So what is capture effect? So capture effect actually, if the input noise, capture effect. Next one term is capture effect. Capture effect. So if the in case of FM demodulator, if the input input of the source, in case of FM demodulator, if the noise signals, that is the interference signals is weaker, in case of FM demodulator, the input of the FM demodulator, if the interference or the noise signal amplitude is weaker than the signal amplitude, then the noise part is eliminated by the FM signals and only dominate the signal part in FM demodulator. So in case of capture effect, so first if the input noise of the FM demodulator is weak, okay, if the amplitude of the input noise of the FM demodulator is weak than the signal noise, that is the received signal noise, then the FM demodulator, the signal is stronger, then signal is stronger, that is the noise is weaker. If noise noise is weaker than the signal, then noise is eliminated. Noise is eliminated by the FM demodulator, and the signal is dominated into the FM demodulator if the noise signal is weaker. Okay, so here the three cases are there. That is, one case is noise is weak, one case is noise weak, and in case of noise weak, then signal is dominate into the FM demodulator. Signal dominate means noise is eliminated. Okay, this is one case. Now another case, if noise is stronger, noise is stronger, then in this case noise is dominate into the FM demodulator and signal will be eliminated. Okay, and another is the if noise and signal both are equal. If noise and signal both are equal, if noise and signal is almost same, then the demodulator input signal is fluctuating from noise to signal amplitude. Okay, that is the fluctuating signal. That is, demodulator input is fluctuating this signal. Okay, and this total effect is known as the capture effect. This total effect is capture effect. Okay, that is, capture effect means if noise signal is weak, then the message, then the receive signal, then noise is eliminated by the receiver, and only the receive signal is dominant. This is one. And if reverse, that is, noise is stronger than the receive signal, then noise is dominant into the FM. And if noise and receive signal both are equal strength, then the demodulator input signal is fluctuating. Okay, and this total effect is known as the capturing effect. Okay, so capturing effect. So this is known as the capturing effect of the demodulator. Now, so another part is pre-emphasis and de-emphasis of the pre-emphasis and de-emphasis of the FM demodulator. So pre-emphasis and de-emphasis. In FM. So what is pre-emphasis and what is de-emphasis in FM? So pre-emphasis and de-emphasis. So first, pre-emphasis. So actually in case of, so if we see the power spectral density, output power spectral density at the FM demodulator, then you can see that power spectral density is look like this. So this is the power spectral density of the noise at the S of NOF W minus W. So this is the PSD of noise. PSD of noise. And if we see that PSD of signal, then you can see that. So this is the PSD of signal. So minus W plus W and S of MF. So this is the PSD of modulating of the message signal. There, so PSD of noise signal and PSD of the message signal at the output of the, so both are output of the FM demodulator. So at the output of FM demodulator. Output of FM demodulator. So This is the PSD of noise signal at the output of FM demodulator. Output of demodulator means after low pass filter, LPO. Okay. And PSD of message signal. Okay, so if we compare these two PSD, then you can see that at higher frequency, the noise is more dominant than the message signal at higher frequency. That is at higher frequency, but in lower frequency, just reverse. The message signal is more dominant than the noise signal. Okay, so as a result, some distortion are there at the output. Okay, so in case of if we compare the PSD of message signal and PSD of noise signal at the output of the demodulator, then you can see that when the frequency is high, that is at higher frequency, the noise signal spectrum, that is the noise is more dominant than the message signal. Okay, so as a result, the output has some distortion and in the FM demodulator. Now, to remove this or to overcome this problem, we have artificially boost up the message signal at higher frequency. Okay, so artificially boost up this higher frequency by using a filter, and this filter is known as the pre-emphasis filter. Okay, so pre-emphasis filter, that is artificially to boost. So pre-emphasis is used in the transmitter section. That is before transmitting the message signals. So we have to boost up the amplitude of the message signal. Amplitude of the message signal before transmitting the message. So, and this boost up can be done by using a filter, and this filter is known as the pre-emphasis filter. Okay, and the same the reverse process is done in the receiver section, and that can and decrease the enhanced amplitude of the receiver, amplitude of the signal at receiver, and this is known as the de-emphasis. Okay, so de-emphasis and pre-emphasis. So in case of FM system, so first boost up the message signal by using the pre-emphasis. So pre-emphasis is filtered, and the reverse process is done in the receiver section, so that the noise is not dominant at the output of the FM demodulator. Okay, so this process is known as the pre-emphasis and de-emphasis. So pre-emphasis that is that is in case of transmitter section, FM transmitter. So first we have to boost up the message amplitude by pre-emphasis filter. So pre-emphasis filter, pre-emphasis pre-emphasis filter. So message signal pass through the, so this is message signal, and this message signal pass through the pre-emphasis filter to boost up the its amplitude level at high frequency, and then it is passed through the FM transmitter. So FM transmitter, and after transmitting this signal, so this transmitted, and in the receiver section, so here WT, that is the noise, is added with the signal ST, and then it is passed through the FM receiver. So here BPA band pass filter, and then it is passed through the FM receiver, FM demodulator, and then output of the FM demodulator is passed through the de-emphasis filter. and then output signal. Output signal. So DMPCC filter. So H of PE, PMPCC F, and here this is the transfer function is H of DE F, and obviously H of DF, this is inversely proportional to H of PF. So minus W to plus W. So H of D is the transfer function of DMPCC, and H of P is the transfer function of the PMPCC. So in this way, so that it can boost up. So actually noise at the output of the FM demodulator at higher frequency, the noise is more effective than the lower frequency. Okay. So that it is artificially boost up the message signal by using a PMPCC filter, so that the noise affected at the output signal is less affected by the noise. Okay. So less affected by the noise, and in this case the power spectral density. So in this case the power, so PSD, power spectral density of message signal. So power spectral density of message signal equal to this one, that is minus infinity to plus infinity, that is mod of H of P F square SMF df. So actually PMPCC filter is selected so that the average power of the MPCC message signal. So here actually the M of T, that is, this is the MPCC message signal. MPCC message signal, that the PMPCC filter is selected so that the average power of the MPCC message signal M1 has the same average power of the original message signal. So average. So this is the MPCC message signal. The average power of the MPCC message signal is same as the average power of the original message signal. So pre-MPCC filter, pre-MPCC filter is designed in such a way that average power of the MPCC filter. So this is the MPCC filter, or the average message signal that of the MPCC, that is MPCC message signal. The average power of the MPCC message signal is same as the average power of the original signal. Okay, so this is actually the MPCC message signal. So MPCC message signal. So the average, so the PSD of message signal. So PSD of message signal, that is MPCC message signal. PSD of MPCC message signal. MPCC message signal is same as the PSD, the average power. This is the average power of the MPCC message signal. Average power of MPCC message signal is same as the average power of original message signal. That is HPFSM, this is equal to minus infinity plus infinity S of MF df. Okay, so the average power of the MPCC message signal MPCC message signal is equal to the average power of the original message signal. Okay, so So this one, and here the improvement factor. So improvement factor I equal to, that is improvement factor I equal to the average output, noise power, average output noise power without pre-emphasis filter. Without pre-emphasis and de-emphasis, divided by the average output noise power, with pre-emphasis and de-emphasis. So average noise power with pre-emphasis. So actually average noise power without pre-emphasis, you know this average noise power. So average noise power without pre-emphasis is equal to. So this is the so average noise power without pre-emphasis is the de-emphasis, and this is equal to the improvement factor. I equal to improvement factor. So what is the value of I? The average output noise power. The average output noise power without pre-emphasis and average output power with pre-emphasis. And this ratio is the improvement factor. Now what is the value of this ratio? Now this value can be obtained. So average noise power. What is average noise power without pre-emphasis? The average noise power without pre-emphasis is equal to this one. Average noise power. This one. This is the average noise power without pre-emphasis and de-emphasis. That is 2 N0 WQ by C AC square. So this is the average noise power, average output noise power without pre-emphasis and de-emphasis. That is 2 N0 WQ by C AC square. So this one. That is, this is equal to 2 N0 into WQ by 3 AC square. This is the average noise power without pre-emphasis and de-emphasis. And average noise power with pre-emphasis and de-emphasis, average noise power, the same as only this one, that is N0 by AC square N0 by AC square, and here actually F square, instead of F square only the de-emphasis filter is there, that is N0 square by AC square into minus W2 plus W F square into de-emphasis filter, that is H of D F. So this is the average noise power with pre-emphasis and de-emphasis. and de-emphasis. Okay, so this is the noise power, that is n0 square by AC square, n0 square by AC square into minus W plus W F square mod of H of D F square, H of D square. So if we put this value, so this is equal to n0 square by AC square into minus W2 plus W into F square into H of D F square dF. So put this value, that is AC square by n0 square into minus W2 plus W F square into H of D F square dF. So I improvement factor, this is equal to n0 square cancel out n0 and AC square, that is 2 into W, 2 into W cube by 3 into minus W2 plus W F square H of
স্যার একটা এনজিও তো থাকবে।
না এটাতে কি আছে, না এখানে তো n0 নেই, তো এটা বলেছি এটা n0, এটা তো n0 by AC square, তাহলে n0 by AC square only this part n0 by AC square, তাহলে এটাও n0, so this is n0 square, not n0 square,
এসি স্কোয়ার বাই এনজিরো হবে।
হ্যাঁ n0, তাহলে this is the I improvement factor with de-emphasis and p-emphasis. So up to this is the noise calculation of the FM. In case of FM, some of the important part are there. One is the so this one, that is the if CNR, there is a threshold effect. Threshold effect means the value of the CNR below which the value of the CNR below which the output is distorted. Okay, so this is known as the threshold effect. Okay, so due to the threshold effect, the output signal has some distortion. So our aim to minimize this distortion, because for good quality receiver, this distortion should be minimal, and this distortion should be minimum by using the pre-emphasis and de-emphasis. Okay, so pre-emphasis and de-emphasis filter. What is pre-emphasis, de-emphasis filter? Now this is nothing but a filter and which can artificially boost up the message signal at high frequency, because you can see that at high frequency that the power spectral density of the message signal is low at high frequency, but power spectral density of the noise signal is high. Okay, so as a result, some more distortion are occurred at the high frequency in the FM receiver. So to minimize this distortion, so we have to use the de-emphasis filter at the receiver, and same filter which is reversed to the de-emphasis filter is used in the transmitter section. Okay, that is pre-emphasis, that is known as the pre-emphasis filter. So pre-emphasis filter and de-emphasis filter is nothing but one filter which can boost up artificially boost up the message signal and message signal amplitude at high frequency. Okay, so this is the pre-emphasis and de-emphasis filter. And threshold effect always you have to remember the threshold effect is arise in case of envelope detector and in case of FM detector. Okay, but in case of coherent detector, no threshold effect is arise. In case of no coherent detector, no threshold effect is arise. Okay. Only the FM signal and the envelope detector with these two cases the threshold effect is arise. Okay. Capture effect it is nothing capture effect this is nothing but the fluctuation of the input signal of the FM demodulator. That is, if the receive signal amplitude is stronger than the message signal, then receive signal amplitude is stronger than the noise signal, then noise is eliminated and the receive signal will will stronger will dominate into the receiver. Okay, so and this is one case, and reverse will be reverse cases are there. That is, if the noise is dominant. When noise is dominant, now when noise signal power is high, and if both are most equal, then it is fluctuating from two values. Okay, and this total effect will be the known as the capture effect. For good quality receiver, the capture effect should be less because capture effect is not arise in case of good quality receiver. Okay, for good quality receiver, the capture effect should be less. Okay, that is no capture effect is there in good quality receiver. But in case of these are the most important part of the FM signal. Okay, so up to this is the FM calculation. So in your syllabus, so FM noise calculation of FM are there. So you can see different types of example are there. So you can see in your book that is the different types of example. So you have to see that example also. In the, either you can see from the actually mostly I am following from the Simon Atkins book. So you have to see from Simon Atkins book of Simon Atkins. So for noise part, I am following from the Simon Atkins. So you have to see you also see from the Simon Atkins. Okay. So or Sanjay Sharma book you can also see from Sanjay Sharma book, but mainly I am following from the Simon Atkins book. So, but most of the parts are same. Simon Atkins and Sanjay Sharma part are same. So only nomenclature is different. That is, here W is there, where in Sanjay Sharma this is F is there. So this nomenclature is changed, but calculation is same. Okay. So you have to see. So up to this is the noise in FM signal. তাহলে তোমাদের টোটাল যে সিলেবাস কিন্তু আজকে
সিলেবাস তো শেষ না।
হ্যাঁ, সিলেবাস শেষ হয়ে গেল। তাহলে এবার তোমরা যদি ইচ্ছা করো যে আরো ক্লাস করবো, তাহলে তোমরা নিজেরা পড়বে। পড়ার পর যদি রিভাইজ করতে দরকার হয়, তাহলে সেটা আমাকে বলে দেবে, রিভাইজ করবো যে কোনো চ্যাপ্টার। তো সেটা তাহলে আগে থাকতে বলে দেবে, আমি তাহলে সেই চ্যাপ্টারটা রিভাইজ করবো। তাহলে ফার্স্টে আমরা কি করেছিলাম না, ফার্স্টে আমরা করেছিলাম যে মডুলেশন। তাহলে মডুলেশন, তো in your syllabus first chapter is modulation. So modulation, then transmitter and receiver, and then the noise in CW modulation.
probability random signal।
হ্যাঁ, নয়েজের মধ্যে কি হচ্ছে, নয়েজ ইন সিডব্লিউ মডুলেশন এর মধ্যে আছে কি না, প্রবাবিলিটি ফার্স্ট the calculation of because noise analysis. So actually this is the analysis of noise in CW modulation. So and noise, so for analysis of noise we have used one mathematical tool. This is known as the probability. Okay, so probability, and also noise is the random signal. So random signal. So for random signal analysis we have used the probability. So random signals and different types of random signal, and also the random process is also discussed. Random process. So random process. So random signal, random process, probability, and after that I have discussed the noise parameter calculation. Noise parameter calculation. Okay, noise parameter calculation, and then I have discussed the analysis of noise in CW models. Okay, so in case of so this is the total chapter. Actually, this chapter consists of 3 parts. One is probability, random signal, and random process, and another part is noise and its parameter calculation. And third part, noise analysis in CW modulation. So this part. And transmitter section, we have also here the transmitter. So different types of transmitter section are used. So just you have to discuss only the AM transmitter, but not bother about the FM transmitter, because this is not required. But receiver section is most important in case. Receiver section is most important. So you have to discuss the receiver characteristic and different types of receiver. Okay, so super Heterodyne type receiver and tuned radio frequency receiver. So 2 types of receiver are used, and different types of receiver parameter, that is the receiver characteristic, image frequency, sensitivity. So these are the receiver characteristics. And in case of modulation, we have discussed the 3 types of modulation. One is the amplitude modulation, another is the angle modulation, and another is the pulse modulation. Amplitude modulation, angle modulation, and pulse modulation. So we have discussed this one. Amplitude modulation. So amplitude modulation are different types. That is conventional so DSB, DSC with carrier. With carrier. With carrier means conventional AM. DSBSC with carrier. DSBSC with carrier, and without carrier means DSBSC. Okay, DSB OSC and conventional AM, SSB, DSB. Okay, and angle modulation, narrowband FM, and wideband FM. A pulse modulation, PPM, PAM, PPM, PPM, and PWM. So these are the total syllabus of DSBSC, AM, SSB, DSB. So this is the total syllabus details. Okay, so third portion. So this is total syllabus. So so I have completed total syllabus. So your total syllabus is completed. So you have to study yourself of this syllabus, and then if there is any problem, then you can tell me. I will discuss that portion in detail, or I will repeat that portion. ঠিক আছে, তাহলে তোমরা বলে দেবে যে হ্যাঁ
স্যার আমাদের এক্সাম কি স্যার আগস্টের 1 থেকে শুরু হচ্ছে?
হ্যাঁ, মোস্ট প্রবাবলি আগস্টের 1 থেকে শুরু হবে। এখনো তোমার টাইম আছে, ধরো 1 সপ্তাহ 1.5 সপ্তাহ টাইম আছে, 2 সপ্তাহ, প্রবলেম হবে না। তো এই 2 সপ্তাহের মধ্যে যদি তোমাদের কোনো প্রবলেম থাকে তাহলে আমাকে জিজ্ঞেস করবে, আমি বলবো। তাহলে ওটা জেনারেলাইজ করে নেবে, সবাই সেটা জেনারেলাইজ করে নেবে, আমি তাহলে ক্লাসটা নিয়ে নেব। ঠিক আছে, তাহলে হ্যাঁ, তো আপ টু দিস, তাহলে টুডেস ক্লাস ইজ এন্ডেড আপ টু দিস। তাহলে তোমরা এটা সাইমন কিংস থেকে পুরো দেখে নেবে আজকে পোর্শনটা, এফএম সিগন্যালে আরো তাহলে ক্লিয়ার হয়ে যাবে, মানে সাইমন কিংস থেকে করলে আরো ক্লিয়ার হয়ে যাবে। ঠিক আছে তাহলে so today's class is ended.
থ্যাংক ইউ স্যার
Thank you.
থ্যাংক ইউ
Hmm.
Thank you, sir.